Okay, so to determine the geometry of a molecule, because of course these are things we can't see. There's no microscope in the world powerful enough to see a molecule. There actually are starting to be things that allow us to get fuzzy shapes of them, but it doesn't allow us to see geometry the way we're going to look at it. So figuring out the geometry of any molecule takes testing. It takes into consideration the bond angles that we're going to be looking at, and that's actually how they used to figure out a lot of geometries. It was bouncing X-rays off of materials and then checking to see what the angle between two atoms was. The thing is, the electron configuration of the atoms involved changes the shape of the molecule. The way it does that is what we call Vesper theory. And I don't know how people actually pronounce it. I've been saying Vesper my entire adult life. Valence shell electron pair repulsion. I think most people say Vesper. And what this says is that any two sets of valence electrons are going to push on one another. They're going to repel one another. So that means that they want to be as far away from one another as possible. So if you have a central atom, like carbon, bonded to chlorine. Let me make this a nice dark gray. Well, that's a terrible example. Oh well. All of those valence electrons on those chlorines want to be as far away from one another as possible. This is, of course, carbon tetrachloride. Nasty, toxic stuff. They want to be as far apart from one another as possible. Now, what I've drawn there is in 2 dimensions, of course. But these things aren't existing in 2 dimensions. They're existing in 3. So this gets us into some kind of odd stuff, and that's where we're going to start model making. So the big question is, how do you get 4 things as far apart from one another as possible when they're all hooked to a central atom? What is the farthest apart they can get? Well, the farthest apart they can get looks a little bit like this. Start adding these. The one purple bond doesn't mean anything, it's just what I grabbed. That's as far apart as those 4 things can get from one another. Well, what Vesper theory gives you is the arrangements, and that one, by the way, is tetrahedral, something that has 5 atoms. It gives you these known geometries. So if you've only got 2 things, a diatomic molecule, they tend to be linear because 180 degrees from one another is as far apart as they can get. And that could be 2 chlorines bound to one another, 2 fluorines bound to one another. When you've got 3 atoms, oh, and a note about this notation. That's notation you're going to see on the lab. And A references the central atom. You should be writing this down. A references the central atom. B is anything attached to the central atom. Okay. So everything has an A. Some things have 1 B. Some things have 2 Bs. So here we have 1 central atom and 2 things attached to it. We have an AB2. And a straight line is as far apart as those things can possibly get from one another. So whatever electrons are on this thing are going to be as far apart as possible. If you have 4 atoms, if you have 1 central atom and you have 3 things attached to that central atom, you have an A, B, 3. And the farthest that they can get away from one another looks something like this. It looks like a triangle. You're going to build several of these. It's called trigonal planar because while it's a triangle, it's also all on one plane. It's flat. And then when we have 5 atoms, when we've got one central with 4 things attached to it, we get what's called a tetrahedral arrangement. It forms a tetrahedron if you sort of fill in all the sides. That's an AB4. So the central atom just sits there, and everything around it tries to attach in a way so as to be as far apart from everything else as humanly, well, not humanly, as atomically possible, pushed to the outer limits of geometry. Now here's the question. What if we have unshared pairs? Because you've already drawn some Lewis diagrams where you have unshared pairs. So water is very often drawn like this. It looks like Mickey Mouse's ears. It's got unshared pairs on the central atom. So there are some molecules that have unshared pairs of electrons on the central atom. It doesn't matter if there are unshared pairs on the outermost atoms, but on the central atom they actually change the geometry. Because those unshared pairs act like another atom. So they push everything else the same way another atom with electrons on it would. So what you have is water, instead of being linear, like that, those unshared pairs, and in the kits, there are little paddles that represent unshared pairs on the central. They deform the atom. If you couldn't see these, it would look like this was bent for no reason. It looks like there's empty space pushing on those hydrogen atoms. There isn't. There are actually 2 unshared pairs. Now the funny thing is, this is exactly the same as tetrahedral. It just happens that instead of all 4 of the things attached being atoms, 2 of them are unshared pairs. And you guys will have a chance to make those. Now, we have notation for this too. So where CH4 or CCl4 was an AB4, because it had a central atom with 4 things attached. That would be this. Central atom, sorry, I'm throwing carbon tet at you. 1 central atom, 4 things attached. In the case of water, how many actual atoms? So we have a central atom, that's an A. How many atoms are attached? 2. 1, 2. So A, B, 2. But there's something else that's changing the shape of this molecule. What is it? What's changing the shape of the molecule? Those. The unshared pairs on the central atom. So we note that when we're writing down the geometry. And unshared pairs are shown as an E. Unshared pairs only on the central. We don't care about unshared pairs on the outer electrons. And so there are 2 unshared pairs. That's an AB2E2. And you're going to get a lot more practice writing those. And your lab packet has got a whole section on that. So the interesting thing, well, you know what, maybe we talk about this. Hopefully we have an hour together tomorrow, honestly. I would really strongly, maybe we talk more about the hybridization after you do the lab. Okay, so with the information you've got at this point about the geometry, what I'm going to do, and you are welcome to go to your lab tables. You're also welcome to work at the regular tables on this. But you will work in groups. I don't know. I'm not counting. Just pass them. And of course, you guys are shy. A couple of friends. That might be 4. It might not. Thanks. So what you're going to do for each of the things listed, let me just walk through the instructions with you. And I would suggest that each lab group grabs 2 kits. A short one? Okay. I would suggest that each lab group grabs 2 kits. Here, can you pass that other one across the back? Grabs 2 kits for each substance listed. Hey, look, you've got a sheet here with columns for your Gooch math to reinforce the Gooch math. Then you're drawing Lewis structures. And all the way down to NH4 1+, these conform to Gooch math. You'll notice that's as far as the Gooch math goes. After you get to NH4 1+, we're going to talk about nonconformers. So, for each compound, this is really important. I do not want you to do all the Gooch math, then do all the Lewis structures, then build them all. I want you to work with one compound at a time. So, do the Gooch math, draw the Lewis structure, then you're going to actually build the darn thing. You're going to take a picture of your constructed model next to your Lewis structure. And then you've got this final data table. So looking at your Lewis structure, looking at your constructed model, you're going to fill in the total number of effective pairs. That's everything that's attached to the central, all your B's. You're going to fill in the number of unshared pairs on the central atom. And you're going to write that arrangement, AB2, AB2, E2, whatever it is. You're going to measure the angle on your constructed model using a protractor. So you actually have to get out a protractor. You actually have to physically measure the angle. And then you can go to your book, and on page 186 there is a chart that lists the shapes for all of the AB configurations. So, you know, AB and AB2 are linear. What is AB3? What is AB4? What is AB5? Okay? And you'll find the names of those shapes. Don't just make them up. It's a triangle. It's a jack. No, there are real names for them. Why do I say that? Because I've had it done in the past, clearly. I'd call this, I don't care what you would call it. It is called a bipyramidal whatever. So anyway, you'll use the page in your book to do that. And I'm going to let you get started on this. If you are a little shaky on the Lewis structures, honestly, doing this lab will give you lots of reinforcement. I don't think this is going to be an issue today, but do not go beyond NH4 until we've talked. Okay? That's what we've got.